Alright, this is part 4 of our lesson about polynomials. In this video we will start with how to determine algebraically whether a function is even, odd, or neither. We're talking about symmetry here. And we will also look at graphs and determine how we know by looking at the graph whether a function is even, odd, or neither. That'll go pretty fast, so we'll probably have time to also solve a nice system of polynomials. Alright, but first things first, number 9. So here's how you determine algebraically whether a function is even, odd, or neither symmetry. Actually, first, let's just at a glance decide. And just at a glance we can know if it'll be even, odd, or neither, because if it's going to be odd, then all of the exponents have to be odd. So I see the 5, the 9, the 3, those are all odd powers. But what about the x? Well, yes, that's x to the 1 power, and that's also odd. So we know it's going to be odd. Alright, but if you just write odd here, you're not going to get any points, because we're supposed to prove this algebraically. So here's how you do that. First, you put a box around this function. Very important, because that's the original function, and we're going to be comparing back to that in a minute. Next, you need to generate the opposite function, which would be negative f of x. And that's just the function you would get by multiplying by -1 through everything. Alright, so that would give us negative 4x to the 5th power plus 3x to the 9th power plus 2x to the 3rd power minus x. And let's put a box around that as well. Alright, we'll be comparing back to that in a moment. And finally, what we always do is we test out what we get if we do f of negative x. In other words, if we take the original function and we substitute all the x's with negative x's. So this would become 4 times negative x to the 5th power minus 3 times negative x to the 9th power minus 2 times negative x to the 3rd power plus negative x. Okay, so let's simplify this. Now we have learned that if you raise a negative number to a power, to an odd power, it stays negative. So all of these negatives inside of these parentheses, they're being raised to an odd power. So all these negatives are like -1s, and those negatives are going to stay negative because it's an odd power. If they were even powers, we could just erase them. So because these negatives will stay, then this is going to become negative 4x to the 5th power. Alright, it just comes out front. This negative is going to stay, but that means we'll have a negative times a negative. So that'll make a positive 3x to the 9th power. And this negative will stay, and again, a negative times a negative is a positive 2x to the 3rd power. And this negative will stay, but a positive times a negative is just a negative, so this will be minus x. And let's go ahead and put a box around this so we'll know what we are comparing to what. So we look at our f of negative x, and we compare it back to the original function and the opposite function. If it matches, if it's the same as the original function, then that means that it's even. If it matches the opposite function, that means it's odd. If it matches neither, then it's neither. So what's the case here? Well, obviously it's not the same as the original function. But looking at the opposite function, we have negative 4x to the 5th power, positive 3x to the 9th power, 2x to the 3rd power, and minus x. Every term is the same. So since f of negative x equals negative f of x, it's odd. And we can just write that down, just what I just said. We can say since f of negative x equals negative f of x, it is odd. Alright, that's how you determine algebraically. So let's press on to number 10. Does the graph represent an even, odd, or neither function? Alright, well, looking back at old lessons, please remember that a function has even symmetry if it has y-axis symmetry. Okay, if the y-axis splits it right down the middle, mirror image on the left and right, that's an even function. On the other hand, it will have odd symmetry if it has rotational symmetry about the origin. In other words, if I take this function and I rotate it 180 degrees upside down, okay, I'm going to let it go now. Poof! See how it looks exactly the same even when it's upside down? If it weren't for the numbers being upside down on the label of the graph, you wouldn't even be able to tell that I really turned it upside down. Okay, in fact, I'm going to hit Control Z now. Watch how it stays the same. Boom. Okay, that's what odd symmetry looks like. That's how we know this is an odd function. Alright, so what's going on with this graph? Well, clearly this has even symmetry because the y-axis splits this graph right down the middle, mirror images on the left and right side. So this is even symmetry. This is an even function. I don't see the answer line, so I guess we can just write it anyway. Alright, let's press on to number 11. Now we are to solve the following system of polynomials. Now please understand that a system of polynomials is a set of two or more polynomials. Okay, so here I have two polynomials together. That makes this a system of polynomials. Now solving a system of polynomials means finding the intersection points. So that's why we always think about what we have graphically. So I see this is degree 4, and in general a degree 4 function is going to look like this, you know, sort of some type of a W type shape. Alright, I mean there are exceptions, but in general this is what a degree 4 function does. And it's a positive leading coefficient, so I even know it will be upward facing like this. Now on the other hand, we have this y equals 13, which is a very tiny polynomial, but yet a polynomial nonetheless. Y equals a number is a horizontal line. Okay, so it could be like this, alright, a horizontal line just like this, and if so, then we would have two solutions, okay, like here and here. On the other hand, maybe it would intersect more like this, okay, and if that were the case, see if I can get rid of those little extra dots. Alright, now in this situation I would have four solutions. Okay, and depending where I put it, I could have one solution or two solutions or three solutions or four solutions. Okay, but this is what it means to have solutions. It's where the two functions intersect each other. We'll give you the solutions. And these solutions will be ordered pairs like 2, 3 and 5, 3. Well, I guess in this case it would be 13 if I want to be more specific. Anyway, I need to give you the big picture because when my students took this test a couple days ago, there's a problem coming up, problem number 14, where they're supposed to sketch a system of polynomials that has 3 solutions. My students really just did not understand this question, so I'm hoping that as I do the problem we're working on now, you can understand that a system of polynomials is like this picture of more than one polynomial. So for example, if I had a quadratic and then I had, let's say, a cubic, okay, this would be a system of polynomials that I just drew. Now how many solutions would this system have? It would have 2. right here and here. So for this problem I was supposed to draw a system like this, but I was supposed to come up with one that had 3 solutions. And of course we'll deal with that when we get to it, but connections, it's all about connections. Is this one we're on? No, that's inequality. Okay, so anyway, to actually solve this, it's pretty simple. We will just do substitution. So I'm going to take this y equals 13 and I'm going to substitute it for y right there. So that makes this a pretty simple problem. Okay, so that means I will have 13 equals x to the 4th power minus 5x plus 7. So my first move would be to subtract 13 from both sides. Okay, so that's going to give me 0 equals x to the 4th power minus 5x minus 6. Alright, so let's go ahead and put this function into our TI-30XS multi-view to see if we can find any zeros on the list. Okay, great. So we're doing the table function here, and I've got x to the 4th power minus 5x minus 6. So I've got x to the 4th power minus 5x minus 6. And I hit enter. I always like to start off at -10 because it rarely goes past that. So that's what I'll do now. Okay, -10. Alright, so I'm just going to scroll down. I'm looking for 0 on the y side. Oh, and look, there's one right there. So there's a 0 at -1. Just while I'm in here, let me see if I can see any more. There's another one. So there's a 0 at -1 and 2. Okay, so let's just jot that down while we're thinking about it. Okay, so zeros. Okay, -1 and 2. Good to know. Okay, so in fact, while I'm at it, I should have just done it this way. So we know that -1 and 2 are both solutions to this equation. But we need to be sure that these are the only solutions to this equation. Looking at the degree, we know that there are 4 zeros, but maybe the other 2 are imaginary, so we don't have to worry about them. But maybe they're not. Maybe they're just fractions, and so they wouldn't show up on our list. Couldn't talk for a second there. So I'd like to graph this and just see, what kind of a graph we're looking at. All right. So let's also go ahead and put this in our graphing calculator. Take a look. Okay, so we had x to the 4th power minus 5x minus 6. Alright, let's graph it up. Let me put it back to a normal window. Okay, so this is what we're dealing with, and so it is now clear that there are only just the 2 zeros. Okay, it's not intersecting anywhere else. Please understand that when we are solving a system of polynomials, we are looking for intersection points. Okay, so we've got this quartic, all right, this 4th degree graph that's doing this type of a thing, and we've got this horizontal line, and it is intersecting in 2 places. All right, so the solutions to this system will be the ordered pairs, the points where they intersect. Okay, so it's going to be like -1 comma something, because that's one of my x values, and it's going to be 2 comma something, because that's my other x value. So we could really think of this in terms of a t-chart. So we have x and y. Okay, so we've got -1 and we've got 2. We need to find the y values that go with it. So the way we find y values is we look back at the original equations. Both of these are set up to give us y equals this, y equals that. Obviously y equals 13 is the simplest equation, so let's use that to find some y values. Okay, how can we use it to find y values, you say? Well, if y equals 13 is the entire equation, that means y equals 13 no matter what. It doesn't matter what the x values are. So, oh, you got -1? Yeah, the y value is 13. Oh, you got a 2? Yeah, like I said, the y value is 13. So that means our two solutions are -1, 13 and 2, 13. Alright, which makes sense. It's a horizontal line. Of course, all of the y values will be 13. So that's it. These are the two solutions. I just feel like recopying it over here. -1, 13 and 2, 13. Alright, so that's it for number 11, and that's long enough for this video. So let's go ahead and stop it there, and we'll pick up with the next video with solving inequalities. We'll be solving and graphing that little guy. Okay, see you on the next video, people.